Welcome to our video for Form Intelligence Algorithm Visualization for Computational Intelligence Homework 2. The simulation that we have selected is for slime mold, namely Physarum Polycephalum. What it does is that even though it does not have a brain or central intelligence, it can solve complex network optimization problems using agents, simple agents that follow simple rules, as is seen in Swarm Intelligence. In 2010, researchers placed food in a map of cities around Tokyo, and the slime mold showed, in fact, it was able to achieve independent networking across it that emulated their rail stations, the network of rail stations that they have there. How does that work? We can have a peek into that in this simulation. So immediately you can see that there are cyan agents that are spreading from the base, the peak base, that is their home. We have another entity, which would be food sources. I'm going to show you how that looks like. It looks like these. These deposit chemical, and what happens when an agent reaches there, as you can see over here, is that it is attracted to it, and as the agents move, they also leave chemical so that you have a trail. And whenever it reaches food, that trail is reinforced because more agents are encouraged to explore it, so you get a positive feedback loop. And this is essentially how you can start off with some sort of network. Now, let's talk about decay. Decay rate shows how long trails persist. If the decay is very high, what you get is something like this, where you get something that's very, you can say, it is smeared. It is not clear. The trails themselves are not defined. They look more like steam in a way, something similar to how you see in mold. But as I lower it, and I'll show it in front of you, you can see that the trails that are not actively enforced beside them, they fade away. And you're left with these very thin trails. It's very similar to pheromone evaporation in ACO, which prevents the colony from converging too early into suboptimal solutions. Now, if I reset, in fact, I'm going to set this as a higher value in general, and I'm going to now decrease diffusion rate. What happens now is that you have much more well-defined sort of paths. If I have these sort of interesting things going on where you have very thin trails. This encourages exploration, as you can see. There's a lot of exploration going on, and it is also somewhat efficient, so you can also see these loops that happen. However, if I were to increase it, these trails will now broaden and now they look blurred. They are not. How this improves efficiency, as you can see, it closes that loop very fast. It's going to close this one very fast too, but it also means that you're exploring far less. So this is something that tunes your exploration and exploitation. Now, if I were to give it, let's say, a low-ish rating, something in the middle, and now let's check sensor distance. What is sensor distance? It is essentially how far ahead the agent can look. Now the agent can't look very far, which means it is mostly trapped at the beginning because it is now distracted essentially by trails that are very close. They're basically blind at this point. But if I put them too high, then what happens first of all is that you will see a lot of chaos. But while they do go outward, they become less inclined to explore once these trails form. So once they form, they see a trail and they just follow it. So the sensor distance does not become of much use. But it is certainly better than going blind, so we should keep this as a high value. Now, we talked about distance. We should also talk about the angle, which is the field of view that each agent has. If I were to keep this very low, what happens now is that it can only go towards trails that are pretty much directly in front of it. So as you can see, only the agents that were very close to the food were able to get to it. So it does seem to work quite well, as you can see that because the exploration was quite high, it was able to converge quite fast. But we will see the dangers of having a very big sensor angle. If it's very large, you get this happen. Now the trails are much wider. It's essentially not optimizing in any sense. Now you can see that the efficiency is quite poor. And this is what happens if I were to do it from scratch, because now it can look behind it essentially and becomes trapped in the beginning like an electron orbiting a nucleus. So we want to keep this low essentially so that you're able to explore. Rotation angle is how much your agent can rotate. If I were to keep this very low, what happens now is that you will see arcs when it is trying to go. Like over here, you'll see there are these pronounced arcs. Since it was already low, you saw that earlier as well, which means that it is able to quite efficiently and smooth, well, not efficiently, but will go to the food sources quite smoothly. If I were to make this very high, what would happen now is that now you see this extremely sharp turns, which makes things more chaotic. And because of that, now what we have is we have these sort of traits that do not seem as well defined and a lot of confused ones. So we would also want to keep this somewhat low. Now let's talk about some presets that I created. One is a dense web. You will see immediately that it looks like a web and kind of like how you'd expect slime to look like. However, unlike earlier, when we were looking at this case, because everything else is tuned accordingly, you now have a good amount of exploration. And due to the nature of diffusion, it is now converging onto very efficient paths, straight lines, as you can see here and there. But once it's formed those paths, it's very unlikely it's going to change, so that's a disadvantage. On the flip side, you have thin networks. As you can see, now you can see each agent, and the exploration here is very good. But the problem is that because they are unable to hold the trails, it cannot go back home, which means it's now lost when it gets out, which essentially breaks up the network. And finally, you have something that's more chaotic, where you will see agents that are not as well organized. So they no longer look as much like a swarm, they more look like they are independent thinkers. As a result, this causes poor performance in terms of networking. While you can see it happening, it is pretty much a mess and it is not going to be very effective for much bigger environments. So that was a summary of the simulation. Unlike ACO, which looks for a specific deliverable, a certain solution, a specific one, in this one, the case is more important about the trails and where it is able to connect between them, keeping the path lengths as short as possible while covering as many food sources as possible. So it's a fundamentally a very different problem, but it is inspired directly from nature and it does show up to be quite useful and a very pretty visualization. So that is all for this, and I hope you like it.